Hello everyone. Today we are going to performing the V and inverted V curve of the synchronous motor. This is a panel for performing the V and inverted V curve on the three-phase synchronous motor. So here is the connection diagram for this. This is a three-phase AC power supply is there connected to the direct online starter, input to the direct online starter. Output of this direct online starter is connected to the common terminal of your ammeter. Second terminal of your ammeter is connected to the, this is a power factor meter, M terminal of the power factor meter, which is going to measure the power factor. After this, L terminal is connected to your stator, which is a load. R terminal of the dual output of the R terminal of the dual output is connected to the R terminal of your power factor meter. Y point of the output of dual starter is connected to the Y point of the power factor meter. Also, this same point is connected to your Y point of your load or the stator. Now B point is connected to the B point of the power factor meter. Also the B point is get connected to your M terminal, second M terminal of your power factor meter is there. Okay, so in the also this L terminal of the power, second L terminal of the power factor meter is connected to your B terminal of your stator or the load. And this is arrangement for the excitation. We were provided the 220 volt DC power supply. In order to vary the excitation, we are given the rheostat is there. By varying the rheostat, we are going to varying the DC excitations given to the field winding. So here you can able to see the actual connections are there. This is my RYB three-phase AC power supply given input to your stator winding as per the diagram. So these are the output of the stator windings are there. As per the diagram, this R phase is connected to M terminal of your ammeter, which is having the range of 0 to 10 ampere depending upon the rating of the machine. The second terminal of ammeter is connected to the M terminal. Okay, M terminal of your power factor meter, first M terminal of your power factor meter. After that, this L terminal is connected to your stator, which is a load side, stator terminal. Okay, now this R terminal of your output of the dual starter R terminal is connected to the R terminal of your power factor meter. After that, this Y terminal is connected to the Y terminal of your stator load. From that Y terminal of the stator load, we were connected to this Y terminal, or you can connect this Y terminal of the stator dual starter output to the power factor meter Y terminal, and from this power factor meter Y terminal we can connect to the stator load terminal. After that, this B terminal of the dual output of the dual starter is connected to the B terminal of your power factor meter. M terminal of second M terminal of the power factor meter is connected to your B terminal of the output of the dual starter. L terminal of the power factor meter is connected to your B terminal of your output stator side is there. So in that way we were made the connections of the power factor meter is there. In this power factor meter, here you can able to see we have the different M, L, R, Y, B, L, M. We have the different types of the different terminals are there. This is a three-phase power factor meter is there. On the excitation side, this is a positive terminal, and these are the positive and negative, both are connected to your fixed terminals of your rheostat. Variable terminal of your rheostat is connected to the common point of your DC ammeter, which is having the range of 0 to 2 ampere. Second terminal of the ammeter is connected to your first terminal of the field winding. Second terminal of the field winding is connected to your negative DC. In that way, we were provided the DC excitations to your synchronous machine. Now let us performing the practical. Now let us start performing the practical. Here we were started the three-phase AC power supply. After that, before starting on this starter, we need to make sure that starter is under the off condition. Now we can press the on green so that your dual starter will going to get start. Now your motor is starting. Now take the now turn on the DC excitations. Here you can able to see the exciting current is going to flow. Okay, it is vary. It means DC excitation is given to this. Now to take the first reading, we need to vary the field current. So we'll take the field current of 0.1. Okay, you take by varying the field rheostat, we can set the field current as per our convenience. Here we have taken the 0.1 ampere. To that field current, we have the power factor is a 0.55, which is lagging, 0.55 lagging, and at that time the current is a 6.4 ampere. Current is a 6.4 ampere. So now again, as you are increasing the value of the current, vary the field current. It is 0.2. Yes. Now you can see the field current is 0.25. That time the power factor is 0.95, near about 0.95 lagging power factor. That time the current is a 2.9 ampere. 2.9 ampere. Now again we were increases the current. Now the field current is a 0.35. At that time the power factor is near to unity, and your current armature current goes on reducing to your 2 ampere is there, 1.9 or 2 ampere is there. After that now your current is 0.5 ampere. That time your power factor is unity and your current is approximately 1 ampere is there, or less than 1 ampere. It means that during the lagging power factor, we were initially the excitations was low. That time the power factor is 0.8 lagging. That's why the more amount of armature current. As we are increasing the excitations, the power factor is moving from lagging towards the unity power factor, and armature current is goes on reducing. Excitations are increasing, power factor is moved from lagging towards unity, and armature current is goes on reducing. Now move the power factor from unity to your leading power factor. Now again increase. Okay, now your 0.7 near to 0.7 field current is there. That time the power factor, you can observe, it goes to the leading. It is a near about 0.97, and here the current is a 0. Now as we will going to increase the value of the 0.8, that time power factor is 0.95 leading, and here you can able to observe the current is goes on increasing. Okay, it is a 5 ampere, approximately a 4.2 ampere is there. So in that way, as we will going to vary, as we will going, now we will going to turn off over here. So what is the conclusion of this? As we will moving towards your leading power unity from unity power factor towards the leading power factor, the armature current is goes on again, it is goes on increasing. So if you see the graph of your V and inverted V curve, initially your current is 0.1, your current is your 0.1. Okay, excitation current is your 0.1 is that. After that it is 0.25. Okay, that time if excitation is 0.1 and your armature current is a 6.4, it is a 6.4, it is again 2.9, again 2 ampere, again your 1 ampere, again your 0 ampere, and your again it is goes on increasing 4.2. So in that way it comes like this. Here is your armature current versus your field current, that is called as your graph of armature current versus your excitation current or the field current, that is called as your V curve is there. Now on inverted V curve, initially the power factor is lagging, now it is 0.5 lagging, now it is increased to 0.95, it is 0.99, now it is unity power factor, again it is reducing from unity to 0.97 leading 0.95. In that way your graph of the inverted V curve is there. So by using this experimental analysis we were proved the graph of the V and inverted V curve is there. So as we will going to vary the excitations, the armature current is goes on reducing and power factor is moved from lagging to unity. After once it will reach to the unity, again if you increase the excitation means in overexcited condition the armature current is leading over here. So as you will move towards the leading power factor, again your current is goes on increasing. So hence we were verified the graph of or characteristics of the V and inverted V curve is there. Thank you very much.